Good afternoon, everyone. I'm Dr. Walaiporn Nakpan from Department of Architecture, Faculty of Architecture, and we are proud to host this special lecture called Realizing by Leyuan Frank Jiang. So let me introduce him a little bit for you guys. I have known Frank's wife, Leyuan, from Cadria 2018 workshop in Beijing with Sahakot, and then I met Frank and his wife again a year later here in Bangkok. It was already 9 years, and as we say in Thai, the world is round or the circle is small. Frank just joined XJTLU Liverpool 3 years ago, and his dean was my good friend. He's German, Mark Orush Nobel, and we both fellows of this Cadre organization. So, about Frank, he is assistant professor in the Department of Architecture, XJTLU Liverpool University in Suzhou, People's Republic of China, and he is also founding partner of Jiang Architects with a background of globally acclaimed design firms. He has spearheaded iconic urban and architectural and interior projects. Frank holds a master's degree from Design Research Laboratory, or AADL, at the AA School of Architecture in London. His research is at the forefront of integrating advanced technologies encompassing computational design, digital fabrication, and mixed reality to redefine the boundaries of spatial innovation. And Frank has published papers on topics such as robotic and augmented fabrication, digital tectonics, and space architecture. He also served as a reviewer for prestigious international academic conferences. In addition to his academic pursuits, Frank has led multiple international workshops, fostering collaboration and knowledge exchange among emerging architects. His work has been showcased in prominent venues, museums, and conferences, reflecting his commitment to pushing the envelope of architectural practice. So everybody, please welcome Leyuan Frank Jiang.
Thank you. Thanks to Professor Walaiporn Nakpan for the invitation to have this opportunity to share the work we have done in practice and also in the school to share with you guys the things and the technology, the thoughts behind all these things we have done. So my topic is about realizing. Actually, I come from a background of practice. I previously worked in offices like Zaha Hadid Architects and Ole Sharon offices. And I know that there is a huge gap between practice and research. That's why my focuses of the research will always focus on the how to realize things more efficiently and trying to understand the constraints and the limitations for the construction and how to enable the design. And at the same time, the design should consider the fabrication-aware design methodology inside this working processes. Before I jump into the works we have done, I can give you a brief introduction about my history. I started to work on or get this interest on this materialization, started from the school called the Architecture Association School of Architecture, and particularly the Design Research Lab. And inside this lab, it's quite different as traditional architecture education. Inside this lab, it actually prioritizes the thinking about what is future architecture. How does architecture respond to the coexistence of users and other creatures, and also the building itself? And with these things in mind, the question I particularly interested in is how to realize these designs, right? And then it becomes to a problem about how to materialize things. And with this, this is what I did and in my group. And actually, we are looking at how these new things and new ideas can be realized with the materials research and the connection research. Further on, I worked in an office and tried to extend these knowledges to materialize in more architectural materials like concrete, timber, even steel. But most of them are in small scale. And small scale is rather, it's like a relative small scale because some of them are already like 3-story high, 10 meters high. Like, for example, this one is the sculpture made with stainless steel. It's around like 8 meters tall. But the problem, or the argument we are having in this project is once we start to manipulate these different types of material and topology, we can extend, or if we can extend these things into architectural scale and further free up the hand from designers, right? Then you can actually design and realize complex things that you can never thought about before. And I also worked in more practical projects, and then the focus on this project becomes like the understanding of the constraints in the real architectural industry. The first one is a twin tower 4 meter tall, and with this, the second one is 100 meter tall. And with this, we always keep in mind that the architecture is not just a box. We have to take inspirations, references from nature, and try to get this smartness into the architectural design, and then try to find a way to realize this with the tools, the digital tools, and also the manufacturing tools available. Similarly, in the urban planning projects, the natural thing is again showed very obviously in these projects. The language is consistent, so you will see the relationship between the individual and the whole. They speak the same language and then form a very strong concept in a way. Also, we worked on like infrastructures. In this case, is a bridge. And this is the first project I want to share with you guys. This is a very, very small project. We started, this project was started in 2018, I think. Back then, I think the 3D printing technology, large-scale 3D printing technology is not so available yet. So we just want to test if we can make something really a physical object with 3D printing technologies. But the things and the thought behind this is not just printing something randomly. We are actually looking at, considering what is actually behind the design. So at that time, I think one term called parametricism is very popular. Patrick Schumacher, the director of Zaha Hadid Architects now, and also the founding member of the AADRL. So in his philosophy, he said the architecture should be malleable. By saying malleable, it's basically, I think anyone knows parametric design or generative design, you know this, right? You have some inputs and then your building or your massing, all the design outcome can somehow relate to the inputs. And with this in mind, we were thinking, what is actually different? If this is applied to all architecture, then does it mean like the building in Bangkok will be the same as the building in China or in Europe, right? So we start to think, what is actually different? The difference between this is actually the designer. So we start to think how we can emphasize this design thinking in our design processes. This project was about tea house interior design. And my friend designed the whole interior space, and then I was in charge of this. It's a very small part. It's just a reception desk and a background wall. And because this is a tea house, as we know, at least in China, we know like tea is originated from China, right? At least the Chinese tea. And there is a very popular poet called Leyuan in China. He wrote it's called the poem of tea, and it was the first thing you can find in the history describe how you can make tea. You grow tea, you boil the water, where the water should come from, what temperature, what kind of time you should boil the tea. So we start to think, why don't we look at what he has described in his poem and start to do something with that? And the location where the tea originated is the delta of Yangtze River, and in that area, it's also called the Jiang area in China. It's quite popular with these layered mountains and this Zen garden feeling of this ripple waving effects. Then we think, okay, we can actually create this kind of very intimate places inside this tea house. And then we start to look into the history. In China, this kind of landscape painting is quite famous. And we can actually see and revert back to these things. Like this is the top two are from one painting, and this one is another one. So this one, both of them are collected in the Forbidden City now in China, which is the highest highest level organization in China, in the museum level. So those two are very popular, and we can see a very interesting things that this kind of philosophy is rooted in Chinese culture. You can see from a long time ago and to the closer Qing Tang dynasty, Qing dynasty, Ming dynasty, and also to now. Like if you were in China, in a lot of places, young people start also drinking tea, and it becomes a very popular culture now. And so we trying to create this kind of feeling and inherit this kind of atmosphere into our spaces. Then we took one point from the point Leyuan, and then we start to think in the Chinese traditional poem, you can actually sing. It's like a song. It has rhythm inside, and each character of Chinese is actually always within a box, right? And the percentage of the infill spaces of a character is also carefully manipulated by the poem. So it looks visually pleasing and also sounds very nice. So we start to also generate something from this as well to express the understanding and or the translation, reinterpretation of this. And then we start to take all these characters and the tone into abstract numbers, and then create this kind of reinterpretation, made this into these graphs. And then we reorient them to create this kind of layered mountain feeling. And then also, both of these are using digital tools, right, in Grasshopper. And then we create this feeling. And if you still remember the image we showed before, is exactly what we want to show. And this shows us the power of 3D printing at that time. So we start to think, if we can still using this technology to develop more things. This was published in a journal in China in 2022. And this is an extension of that. Like, this is a project for an exhibition did in Xi'an Liverpool University. This was a design venue, like exhibition venue. So a lot of brands and universities, and also there has a booth for top 100 Thai designer in there. And we joined this venue, and we were given this booth. Sorry, we were given this booth. It's 18 by 4, and the depth is not so big, but we don't want to show like everything just lay there, and you don't have an interaction with that. We want people to move in and actually experience spaces. So now, also another important thing, we have to show some exhibits from our colleagues. Right? It's not just about the booth itself. So we start to, because we are located in Suzhou, if any one of you know the traditional Chinese garden, so this sense of feeling is very strong, is that you are always walking inside like a puzzle. Like you don't know exactly how to go to the other side if you see that. So this kind of feeling is very, we're obsessed with this kind of feeling. So we want to create this kind of similar feeling. And then we start to look at what is actually associated with traditional Chinese garden. Then we took this kind of inspiration also from the nature, like the stone and the water, and also plants, and how the fish is interacting with the lily leaves, for example, lotus leaf, sorry. And then idea come to us. We want to also express the sense of field. So any object has this like power field. So you have like have a relationship and also a reaction between two pieces. Or for example, two of us, we can have like, if you are close to me, and then the feeling becomes very different as you are far away from me. So we started to create a kind of like magnetic field feeling with that, and we use a consistent language to design the ground, and also you can see this kind of like screens, panels, and also the back wall there to define the space and also create the circulation, guide the circulation. We also extend this feeling from the ground, from the overall design to these screens. You can see here. These ripple effects actually create this very vivid feeling about the space. And when you walk inside, it's very experiential. So how to create this? We use the robotic 3D printing in our lab, and they are related to a lot of technical tests, like material, heating, temperature, printing speed, mixture speed, and we also did like material color changing. So this is the final effect we achieved. Couple of sectors about the booth and the reflection we want to create. Because actually it's not a static thing. When you move inside the booth, because of different lighting effects or reflection, you can see the moving pattern of these screens. And it's very nice to hear that all the visitors, when they came, they don't even look at the title. We said flowing Zen garden. They are immediately telling us, wow, this looks like a Zen garden. So this is a very successful project for us. And we got the Idea Design Award, which will be, the award ceremony will be here in this weekend. And we also got the European Product Design Award for this project. Okay, after that, this project, this is a very small research project I did with some of our undergraduate students. Actually, before that, because I came from a firm mostly doing very career things, right? And I found it very difficult to really achieve high quality, even though you're paying a lot of money. And it's very difficult to achieve high quality smoothness inside this construction of the facade cladding. And they looks nice, but at the end, most of the people don't know how they were produced. So in this project, I took some of my students, we went to the factory to understand how these things are produced. And this was doing inside their factory. And they were doing this mold for the concrete. So the glass reinforced concrete panel, glass fiber reinforced concrete panels are sprayed onto this formwork, and then they are shaped. And then after that, they demold and polish the facade, the outside. Within this process, it's very time-consuming. It creates a lot of material waste, and it's not sustainable because all these formwork, they can only be used once. Even though they can be used repetitively, the wooden formwork can only be used twice. So this is a huge waste for this production. And for some very highly repetitive project, they will use the silicone mold. And the silicone mold, in order to make the silicone mold, you have to make the GRP mold first. Then to cast the silicone, then use the silicone. And the silicone mold can only be used 10 times. So in this industry, the waste is huge, and it requires a lot of labor. And inside this factory, I talked to their boss, the owner, and they're saying the only digital part they're using is just to CNC you see these pieces. That's it. All the other things are manually done. So it brings another problem is the precision, right? How you can make sure it's precise if you have huge requirements for the smoothness. And then we start to think if we can use some digital technology to enhance or at least the efficiency, if not the precision. The precision can also be reached only if the designers know how to fabricate it, and then design tailored for this technique of fabrication. Right? In this case, we're using a hot wire that cut through the form and they create this pattern, and then you can cast the concrete inside. After this, we did a test. We cast the concrete inside, and then we did a 3D scan and try to compare to the original geometry. The deviation is very acceptable in this mechanism. The problem, we didn't go deeper into this research because we talked to this glass reinforced concrete companies. They are not sure if they want to continue developing it. We're using this as a proof of concept and ask them if they want to collaborate with us. And this is a short video to show you what we did for this project. This was a very initial testing or experiment we did. There are a lot of parts we can improve. We can keep on working on this, but we didn't do it. We're just waiting for the opportunity to continue on this project. And there are a lot of things we know it's a limitation or constraint in this production method, but I think we can eventually have a method to overcome all these constraints in the end. Because compared to the traditional way, it's more it's a lot cheaper, a lot cheaper, and also very fast. And the mold, if we design carefully, the outer casing mold, similarly to like rammed earth or traditional casting concrete, it can be reused for multiple times. It's more sustainable than the other construction method. And then we also extend this wire cutting techniques to like more artistic pieces. This was exhibited in an exhibition in Suzhou. This building was designed by Pritzker Prize winner Christian Pottenbach. So it's also a very good opportunity for us to showcasing. This is inside the exhibition called Digital Enabling. It's all talking about digital design and digital fabrication and digital experiences. And this project was also an extension from that. This was collaborated with Zaha Hadid architects, and we did the cutting, the material test, the painting test, the finishing test, the beveling test, and at the end I produced this piece, and it was exhibited in the Zaha Hadid Architects Exhibition in Shenzhen. And also now it's exhibited in Hong Kong, Shenzhen Bi-City Biennale of Urbanism Architecture in front of MAD project just recently opened. That project the building was designed by Copenhagen Blow. After that, we were thinking like, okay, you have all these constraints. What if I don't want to consider the constraint? I don't want to do, for example, rationalization, not rationalization, but maybe I don't want to compromise the design. I just want to keep exactly the same design. What do? Then we moved from either casting or spray concrete to directly 3D printing. So this was the roof. This white thing you see, like the ribbon is all 3D printed. So with that, we have to, similarly, it's not so easy, right? It seems like, well, you have all the freedom because it's 3D printing, but you have to consider the constraints for 3D printing. The constraints will be, firstly, is the size of your machine, right? If we are using, for us, we're using a robot, so the size cannot be too big, or it cannot be too small. So you have to consider the constraint for this, and then the constraint for the material itself, because the concrete is still liquid, like more liquid than stone, right? So you have to consider while printing, if it's too slow, then the adhesion between layers will not be so good. If it's too fast, then the initial strength is not gained yet, so the deformation will be very big. And if the pace is too high, then the deformation for the setting will be too big. All these constraints needs very rigorous research on this part, how to print just one piece very like perfectly. So we started with panelizing the whole ribbon, and then we defined the parts like systems. We call it facade systems, right? Divided them into parts of the system, and then we have to actually consider also the efficiency for the printing. For example, in this part, right, we cannot always keep this continuous, because if we cut here, then this piece maybe this part will be, it will have 1 or 2 more pieces, which means you will spend at least 4 to 5 hours more just for that. And then we have to do printability test inside the digital platform to do the simulation. And then we have to analyze all the pieces inside this. This is just one part of that. And then after that, it's proof that inside the digital environment, then we have to do a mock-up test if this is really standing up If not, we have to revise back to a digital platform and do it again. So this is a recursive, iterative process. And this is how we did for the printing. Actually, inside we have the rebars, even though it's not functional so well, but it still like can provide some of the tension for the concrete, which is the weakness for concrete itself. Right, we have to also, if you see this pointing out thing here, because we embedded this connection for the assembly. I didn't talk about the details about tectonics. We spent a lot of time also figuring out how these things can be connected and assembled on the facade, on the roof also. This is a final. So the plastic sheets are curing the concrete here. This is the progress of the building. Now it's finished. The main part is finished. Now it's time to install the panels now. And also collaboration with the same company, we did a 3D printed bridge. It's a very simple way. The challenge for this part, for this bridge, is actually the turning angle printing. So it's not slicing always like horizontally. We have to print like gradually changing degrees. We did not stop just in the practice. We also bring these things into teaching. This was done inside our school, and the student learned all these techniques about how to develop the geometry first, how to develop the printing toolpath, and then how to produce the piece, and then how to cure the material, and at the end how to install them. So after the whole process, they've learned they can actually do something else if it's not about concrete. So the workflow will be quite similar. The thinking method will be also similar. This project is now the following two projects will be the workshop, the international workshops we did in our university. This is the first one. It's called Steel Fusion. It was done in 2024. We have a team of tutors from SciArc at that time, and also AA and Bartlett, and me and another colleague from our university. We had Eagle Pentic and from Studio Eagle Pentic and UCL came for the crit and also guest lecture, and we had Matthew Tam from Karamba 3D and B plus G engineering company to give us guest lectures and also some instruction. We had like 20 students from different universities from Europe, Hong Kong, US, something. And this workshop was based on the previous research I've done for digital fabrication and augmented fabrication. So we extended this workshop to by understanding the material behavior and the constraints about these techniques in the construction, and also built on the previous done projects. So in this project, we actually started from the design to the development and then to the construction. In this process, we always keep in mind that we have to do fabrication aware design. In that case, you can have the best outcome of the design. So the pavilion or the design initiative is very simple shape, and then we generated the path like this for the structure and the panels for the decorative parts. So this will be the final outcome, and we use AI to visualize or to give iterations of design options for our reference, and we also use this to communicate, because this is the space inside the Suzhou Museum designed by GMP, and this is a high-level museum in China. We have to communicate with them very long time before the design is even finished. So to get the support for us to exhibit there. Right? And at the end, we didn't get it. We get this space. This is the, I showed you before, this is also inside the building designed by Christian Pottenbach. And this pavilion was divided into 3 parts mainly. The first part is the outer part is form, cladding, and the structure. The structure consists of the main structure and the substructure, and the base is the wooden part. And we have to, because this workshop is about digital fabrication, then we have to actually generate all the data, all the files to instruct the robots, right, to help us to produce things. And for the cladding, we divide it into 5 parts. We call it 5 trunks, C1, C2, C5. And all these parts were individually produced by the robots. And we don't need to think. We just send the file to the robot, the tool pass, basically. The tool pass to the robot, and the robot generate, and you just put a tag, the label on top of it. And in the construction, you just put them number by number. And in the each trunk consists of the flat panels and corner panels. And this is how the tool path was planned. For efficiency, we also put a couple of them together inside one form block. This is how it cuts and labeled. We also did painting test, right? Some material, some paint will damage the form, some paint or not. Some paint looks nicer, some paint looks bad. So we also did test and then painted. And this is how the structure is consisted. The base, the main structure, secondary structure, and the connector. The main structure was assisted by the augmented reality. So you have the vision inside this headset, so you know the degree about the bending. So when you bend to the desired degree, then you can stop, right? And with the system, then you can bend all the pieces and connect them together. And also for the secondary structure, the substructure is also bended with rebar. So you can see here they are wearing the headsets and connecting them. And for the connecting piece, it's also assisted with this augmented fabrication part. The base was CNC milled. And then here is about the assembly. You can see all the pieces were laid down on the ground. It's a huge work. And this workshop is only 9 days. Right? The assembly at the end took 2 days to assemble all the pieces together. So you can see this from fabrication, from the start of the fabrication to the finish of this project only takes 7 days. So I think it's a huge demonstration for digital fabrication and augmented reality, AR-assisted fabrication, as we're saying. At the end, it's built, but even so, I can show you a short video about this workshop. in this project, it was a great success for us, but we're still thinking it's not enough, right? Because we found some very challenging parts inside this project. One is the precision, because in this project we relied pretty much on give the precision control to the AR. So, and on the other hand, because the facts or the property of this material is elastic, and you cannot really control the bouncing effects of this material. So at the end, because we were facing another huge exhibition, so actually after this we did another one. So these issues are well known. I think this was published everywhere, and still I don't think this can be solved in very short time. This is not, I think it's not inside our scopes already. So we didn't really pay too much attention to it, but in the other hand, we're thinking how we can use design to avoid these problems. And so we did the second version. So compared to the first one, we developed everything, basically. The cutting angle, the workflow of the cutting, how you can custom made a tool for the cutting, for example. And then we found a contractor help us to realize this. And we simplified this, the inner side of this pavilion. So you can see all these things are clearly labeled. And also the sequence about how this can be can be joined all together, and labeled really carefully. And then we even designed the connection method. We involved the the facade engineer also to help us. So all these things were generated in the table and sent to the contractor, and all these things are also generated. And also we made some of the piece modular, so they can produce more efficiently, and they don't need to really consider about the labeling issue. We involved the structure engineer also to help us to rationalize the structure, and then we reiterate the design. So this is what we did for the second version, right? The form cutting is still the same. We did it in our lab, and these aluminum sheets were generated for the backside, and so it's easier to align all the form onto this panel. And then the connector was custom made, and then they were all labeled in the connection parts. So when they produce the panels, they already pre-drill the holes, so you know exactly where it should go. The only flexible part is here. Flexible part here and here. So we can adjust these two and find the desired shape. So these tubes are all produced with a guideline with the files we generated. This is a test assembly inside the factory. And in this process, we altered the use of AR for precision depending to more of a supervision. So you can see if anything goes wrong, you just know, okay, this piece should go there, and then you just fasten or loose pieces on the construction part. And this was exhibited in the World Industrial Design Conference. And also, again, in the Future Labs, it's about the International Education Exhibition in Shanghai Westbound Art Center, which is a very artsy and popular space in Shanghai. And again, in the Suzhou Bay Digital Art Museum, in the building designed by Christian Potzenbach. And these two projects and the workflow was published in two papers. One is Kadria 2025 and ICADI 2025. This is a short video about second version. The hierarchy of this structure is very clear, and it's a lot cleaner, and the precision is really high for this. Then is the second workshop we did in just last summer. We also extended the use of augmented reality, and in combination with the robotic fabrication in this case, but we changed the material. We used bamboo and timber. Similarly, we had 20 students, and we joined by staff from HKU at this time. Instead of producing something very, how do you say, it's like very armory shape, we want to make something like really mimicking this kind of natural phenomena of this kind of feeling swarm and sand dune feeling things. This is also AI generated for our reference for the further design. And then we develop our design. Similarly, we want to do like a second edition for the first workshop. So we use the same starting geometry, and then we deform it a little bit to find the desired shape, like self-stable shape for the pavilion. And we developed the shape with timber main structure, timber secondary structure, and timber frame, and bamboo cladding in this case. We want to test if we can use elastic material in here and try to understand the behavior and use digital tools to simulate the behavior. This is the cladding panels. This is how it consists: the base, main structure, secondary structure, the frame for the bamboo, and the bamboo stripes. Okay, we also divide them. And in this case, we divide them into two parts. One is for the structure, one is for the bamboo. There's a lot of elements inside, if you can see here. These are all produced within a week and assembled. This is the structure. Because they have the timber structure has different angle, and they have to be connected very precisely. So in this process, we use the robot to help us to place for the precise angle for the cutting. And when the robot is pick up the timber elements and place and feed it to the table saw, and one guy can just cut it. This is the workflow. It's how it's working, and place it and just cut. Okay, and in here we have to be careful about the clashing detection. So everything needs to be simulated beforehand before you actually proceed with the cutting. Sorry. And after that, we have a laser cutted steel panel here, and then we use it as a reference to drill the holes. If possible, we can also embed this in the robotic fabrication path, so we can just change the NA factor automatically and drill the holes. These are how they're connected with bolts and nuts. The secondary structure is also timber, and we didn't do the same as the first pavilion. In this case, we're trying to utilize as much as possible for the already made pieces for the connection. So we don't have to produce them. And in that case, we can also lower the budget, and we can build the pavilion more efficiently. And one big benefit for that is we can do disassembly and reassembly really quickly for this one. And before the assembly, we actually use the robot also to help us to detect if the pieces are made pre-made precisely, and if they can come together very well. If not, we will reproduce them. And in this process, we actually use the robot to collaborate with AR vision and also human to see if everything is aligned very perfectly. This video you see here is from the phone. It's not so accurate. So the problem is also with AR is with the HoloLens, the one who the students are wearing on the head is a lot more precise than iPad or iPhone. So, but the problem is this is very expensive. We cannot afford all of them. And then after checking, it's okay. It can be easily assembled. It's precise. Then we move everything to the site and start the construction on site, piece by piece. Okay, this is everything you can see overlaid on site, and you just place these pieces one by one according to the vision. And this is the connection for the secondary structure. After the finish of the pavilion, the structure, you can actually use the AR to check if everything is in position or not. If not, you can take measure to that. The base was also produced with CNC, but in here we actually developed the sequence and how they can be used more efficiently and more precisely, and all the holes are also identified and pre-drilled on the wood panel, and then you can just bring them on site and slot them in the sequence, and they will be easily and precisely connected. This is a sequence about how they should be placed on top of each other. And you can see the connecting piece below is also marked, so you can just place them very quickly. A film was applied to the wood panel, and this is the AR vision about how you place them on site. Bamboo panels. So in this project, we want to test if we can actually use digital tools to understand the material behavior, and then, in a sense, to control the precise curvature about the material. It should be a video. It doesn't play. Okay, it doesn't play. It's okay. So inside the grasshopper, first of all, we get this material, the bamboo stripe, and then we try to push it and to find its balance, the strength. It's not too tight, it's not too loose, just okay to keep the shape. And then we try to get this data and translate it into grasshopper, and then we use this data or the behavior of this material to do the simulation about all the panels. And then we know exactly the length of this material. And then we can cut this material with this number. This is a cutting of the bamboo stripes. We did a serious study about bamboo knot tying. And these are 3 types of what students did. Because for this project, the bamboo panel, they are not rectangular, right? They have an angle, so you cannot really tie it very fastened like this. You have to leave some tolerance so it can rotate. This is a challenge also for this team. And after test, they finalized a mechanism, and then they applied this mechanism to all the bamboo panels. And they did a test, and it can perfectly align. So to attach these bamboo stripes, they have to develop the timber frame. And for this timber frame, because they're all different, again, they also produce the sheets, and then they use sheets one by one on the table. And then they also use AR to guide them how to join them together. So with the correct angle and the correct length. Now this is a simulation showing you how this behavior was kind of like simulated. And then in the real time, these numbers are got to instruct the fabrication of these panels. Once you're tightening up these panels to the frame, it will give you the desired shape. These are all the 27 panels were produced for this project. And then this connection for the frame, the panel frame to the secondary structure using the L brackets, and the location and the touching points are all carefully manipulated in the digital system. So all these things you can see from the AR, and you can just not drill it because the holes are already drilled, so just connect them with nuts and bolts. Right, this is a comparison between the virtual and the reality. These are the final images, the finish of workshop, and everybody is so tired after making this project, so they are sleeping everywhere. And at the end, they decided to hit me. And then this project was also exhibited in Future Lab 2024 for the international education sectors in Shanghai. This project is just accepted by the cadre in 2026. And this is a video to show you the workshop. student, the first pavilion came without any experience in digital design, digital fabrication. And the second one is more or less similar. But some of the students from the first workshop came again for the second one. So those students already have some experience, but most of the students don't have any experience. I think this workflow from digital design development to digital fabrication, augmented reality, assisted fabrication can have a very bright future to instruct the untrained labor to build something very complex. Especially, I think, for the architecture is similar, especially for the facade, cladding, installation, etc. Okay, thank you. That's all for the talk. Thank you. If you have questions, I'm happy to take.
So as someone who uses computer as the main medium to design, I want to know the main limitations that you face currently, like now, that you hope could be improved with future technologies.
I think the biggest challenge I'm facing now is not the design. I think is how to, as I mentioned in one slide, how do you understand fabrication for the design? So you have to keep in mind the fabrication aware design method. If you want to produce something nicely. And I know like there are some crazy design and cannot be realized very nicely. And I think that's a demonstration for your answer. The design is already far beyond the limitation of fabrication. So I think design, you can, I personally, I don't think I have any limitation about design. If you are familiar with AI now, you can design anything, right? But how to make it realize, how to rationalize it, that's the question. Thank you.
So I am curious about what kind of technology would you hope to have in the future to support your design?
I think later, if possible, and I think I'm also trying to do some research on this part, is how to train AI to understand the physical limitations. So, for example, when I design something, crazy shape, crazy scale, and the AI can real-time assist or support, suggest that what kind of things I can do to make it feasible for the construction. That's I think it's the future for me.
Thank you.
Are there any resources or material that you can recommend for someone who wants to pursue in this field?
You mean for design or fabrication?
For fabrication.
Platform? You mean software or?
Anything, books or like digital platform?
I don't know really if anyone is reading books these days, but if you are interested, I think no, some of the, for us, definitely to read research papers, but then it requires a preliminary understanding about this field. I think maybe you can watch some YouTube videos first for the introduction, and then you can find your interest. And once you know, okay, you're interested in this or that, and then you can dive deeper. And also there are some books writing about bio-inspired biomimicry design, and I know in the past maybe 10 to 20 years that architects are obsessed with this term biomimicry, and they want to decode the nature and try to use this smartness. For example, I don't know if you know like topology optimization for the structural optimization part. It's kind of like mimicking what is natural doing, right? So I think maybe you can firstly find your interest, then you will find what you will. I think the resources are plenty. You can easily get them, but you need to know what you want to do first.
All right, thank you.
As I see, there are so many material that you're trying to explain. Yeah, but the thing is, have you ever tried the glass or another type of material, because there has some different like qualities?
Yeah, glass is a fascinating material, and we were asked actually by our dean of our school to develop glass 3D printing. But that is it's very difficult because you need to heat up the whole glass to a liquid state, and then you can print. And then if you do you know MIT?
Yes.
Yeah, MIT Media Lab, right? Neri Oxman, they did glass 3D printing, and the light effects is amazing. It's very nice, and because the glass can be solidified very quickly after it's cooled down, and then which means if you do 3D printing with that, there is a potential that you can create more complex, more exaggerated shapes. But for us, we didn't do that yet, and also I think there are a lot of potential to do with glass for the aesthetic part of view. But for architecture, I don't know what part we can apply this yet. But this is a good question. I think definitely a lot of people will do research of glass later. You will see soon.
Thank you. So in these fields, it's only have the thing that popular, like only wood and also the concrete, right?
No. I don't think the material is a limitation. But why you don't see so many research topics about in the fabrication for material is, I think this material research part is, to me, is one of the most difficult research field when you do with this. And we are actually in our school, we are also trying to develop new materials composed with waste, like for example coconut fiber and like water bottle and these things. And a water bottle, recycled water bottle is already proved it can be worked with robotic 3D printing. And we have a collaborator. And we also did one project. I didn't show it here. We did one project with an industrial collaborator to print some furniture pieces, and that piece was, and that company was specialized using recycled material, and those material, I think, in some part is the recycled material or some other innovative material are more expensive to use than newly produced material. But in some cases are not, but most of the cases we know are in this situation. But yes, that other material are also under a lot of research topics now. And for us, we're also doing 2 or 3 for new material research. But they are not so common yet in the architecture world. That's why you don't see so much about that.
So first of all, thank you for the presentation. I want to ask about, so when you said like with AI and all, like sometimes the design is, you could say, almost limitless. So I want to question about, do you find yourself designing from like the smallest unit, like you have the smallest unit, maybe some materials you want to work with, and its connection, and then you expand it into like a more bigger scale, like a sculptural or maybe even an architectural scale building. Because I feel like when you think about the big picture first and you like try to scale it down, maybe that increase the amount of fabrication error or like limitations. Maybe like working from the smallest unit and expanding is better. Like how you feel about the two methods?
I think for the two methods, we don't have a preferred direction. I think for what you are saying, like a bottom-up way of considering, we are also investigating them. Because if you know, for the AR assisted fabrication, the way you're saying is the best way. Because, for example, we are creating modular systems. And then for the AR, if it's modular, meaning the connection is also modular. And then the precision can be very high. You don't really need to consider the precision problem for the AR system problem. But the outcome of top-down and bottom-up, they will be looking very differently. But I don't think both ways are fine for us. And we just want to create something. For us, in this stage, we want to create something can be scaled up into architectural scale. Like bottom-up view, I don't know if we can create into architectural scale or not yet. But if you are considering something like metabolism, they're also modular, right? And they can create like larger scale. But then once you go into that scale, does this really something what we want? Because when we were studying the modular system, perhaps we are considering the small scale. When you become bigger scale modular system, then under this module you have a lot of other modules that you can consider, right? Then it becomes like architectural elements. So this is something. I mean, if you consider the pavilion we do is just one module, we can replicate them, something like that. But both ways are fine. And I think for a research point of view, that bottom-up is also a very valuable test for us.
Thank you.
If you would do follow up on the pavilion, what would be the next update?
You mean for this one? Now, because I can do very technical stuff, but I don't want to categorize myself to that part. I always want to do more artistic part, or the expression of the things we show. So the next step, we were considering to connect with media art. We want to do a bridge between like digital fabrication and new media art design and how do you call this mechanism development and embedding all these things. Because I know, in China, this new media art is like growing really fast. People are using like Touch Designer and all these softwares to do interactions. And I'm more interested in this human, because this project talking about human-robot interaction. But my interest is about the things we produced, interact with people, how they feel. And I didn't show one project from the teaching we did in last semester is we built one pavilion and then we embedded music, lighting effects, also to interact with the users. And I think if I were to do the next one, and we are going to plan it really shortly, is to embedded interaction. But we're not sure yet what interaction it will be. It can be either visual or it can be like a kinetic thing, something like that.
Thank you. As a token of appreciation, I would like to give you a small gift.
Thank you.
Yes. ถ่ายรูปให้หน่อย